Last summer in Phoenix, Arizona, a family of 4 watched their neighbors spend $400 on a single water bill, while their garden stayed green through a drought that cracked the surrounding desert floor into plates. Their city had imposed outdoor watering restrictions so severe that most residential gardens were simply abandoned. Brown lawns stretched down every street in the neighborhood. Vegetable beds went unplanted because nobody could justify the water cost. The family on the corner kept watering. Their tomatoes kept producing. Their fruit trees kept their leaves. Their raised beds ran all the way through August without a single municipal water connection feeding them. What they were using was not a well, not a rainwater collection system because there was almost no rain to collect, not an expensive desalination unit or a sophisticated filtration array that cost more than the garden was worth. They were using the water their house was already producing every single day and throwing away. The water from their showers, their bathroom sinks, their laundry machine, water that had already been paid for, already been heated in many cases, and that was traveling directly from the drain pipe into the municipal sewer system, where it cost the city money to treat and cost the family nothing in terms of recovery. That water is called greywater, and the gap between what most households know about it and what it is actually capable of doing for a garden during drought conditions is one of the most significant and most deliberately obscured pieces of practical home knowledge available to anyone who owns a property with a drain pipe and a piece of land. The average American household of 4 generates between 50 and 100 gallons of greywater daily. Not weekly, daily. Across a 90-day summer drought, that household is producing between 4,500 and 9,000 gallons of water that flows directly into the sewer system, while the garden 20 feet away dies from lack of moisture. At municipal water rates that have been climbing 3 to 5% annually in most drought-affected regions, the difference between harvesting that water for garden use and sending it to the sewer represents a cost that compounds every dry summer for the entire life of the property. Greywater is specifically the water from sinks, showers, bathtubs, and washing machines that does not contain toilet waste. It is not clean water, and it cannot be used in every application without treatment. But it contains far less biological contamination than black water from toilets. And with a properly designed filtration and distribution system, it can be safely applied to garden soil in ways that produce the same plant growth outcomes as municipal irrigation water while costing nothing beyond the initial infrastructure investment. The reason most homeowners do not know this is the same reason most of the useful building and homesteading knowledge covered in this channel does not reach mainstream awareness. There is no profitable product to sell around it. A properly designed greywater system uses pipe, gravel, sand, and mulch. Materials so ordinary and so inexpensive that no corporation has a margin incentive to market the system to you. The water utility industry has no interest in telling you that 50 gallons of water per day is leaving your house unused when their revenue depends on you purchasing replacement water for your garden from the municipal supply. And the landscaping and irrigation industry that sells you drip systems and spray heads and automated controllers profits from your continued dependence on pressurized municipal supply as the only acceptable water source for residential irrigation. The knowledge exists. The physics is simple. The biology is manageable with basic filtration. And families in drought-affected regions across the American Southwest, Australia, the Middle East, and sub-Saharan Africa have been running these systems successfully for decades. The gap is not technical. It is informational. To understand how the system works and why it works as reliably as it does, you need to understand what greywater actually contains and what the soil does with it when the system is designed correctly. Greywater from showers and bathroom sinks contains soap residue, body oils, small amounts of skin cells and hair, and trace quantities of the personal care products used during bathing. It does not contain fecal bacteria at the concentrations present in black water. It does not contain the pathogens associated with toilet waste. The biological load in shower and sink greywater is low enough that a properly designed soil filtration system neutralizes it before the water reaches plant root zones. The soil itself is the final filter, and it is extraordinarily effective at processing the organic compounds in greywater when the system is designed to distribute water below the surface rather than spraying it through the air or pooling it on the soil surface where evaporation and human contact occur. Laundry greywater is more complex because it contains higher concentrations of surfactants from detergent, sometimes fabric softener residue, and depending on what was washed, potentially elevated levels of phosphorus or sodium that can affect soil chemistry over time. The filtration requirements for laundry greywater are higher than for shower water, and the plant selection for a laundry-fed system needs to account for the slightly elevated sodium content that accumulates with continuous application. Fruit trees, berry bushes, and ornamental perennials handle laundry greywater well. Vegetable beds where edible portions contact the soil surface need shower greywater rather than laundry water, and the distribution needs to be subsurface rather than overhead. Kitchen sink water is excluded from residential greywater systems in most regulatory frameworks because it contains food particles, fats, and oils at concentrations that create anaerobic decomposition problems in soil filtration systems. The grease in kitchen drain water creates biofilm buildup in distribution pipes and can produce hydrogen sulfide in buried systems. Kitchen water goes to the sewer. Everything else from the household can potentially be diverted. The system design that handles all of these variables correctly, that separates shower greywater from laundry greywater appropriately, filters both streams to the level required for safe soil application, and distributes them to the garden in a way that eliminates surface contact and evaporation, is called a constructed wetland greywater system. It is the design that the family in Phoenix was running. It is the design that Australian homesteaders perfected through 2 decades of increasingly severe drought conditions. And it is the design that can be built from hardware store materials for between $200 and $400, depending on the size of the garden it needs to supply. The constructed wetland system works on a principle that every traditional culture living in water-scarce environments discovered independently. Biological and physical filtration through layered media is more reliable, more sustainable, and more effective for residential-scale water treatment than any chemical or mechanical process at the same cost point. A properly constructed wetland filter containing gravel, coarse sand, fine sand, and a biological layer of specific wetland plants removes the biological contaminants from greywater through a combination of physical straining, aerobic bacterial digestion, and plant uptake before the filtered water enters the distribution system that feeds the garden. The biological layer is the component that most DIY greywater systems omit, and that most professional greywater consultants charge significant fees to design. It is also the component that transforms a basic greywater diversion into a system capable of handling continuous, high-volume household water output through a full drought season without the biological buildup and odor problems that characterize simpler systems. Specific wetland plant species, primarily common bulrush, cattail, and certain sedge varieties, have root structures that create aerobic zones in otherwise anaerobic, saturated soil media. Their roots release oxygen into the root zone through a process called radial oxygen loss, creating conditions where the aerobic bacteria responsible for breaking down organic compounds can thrive even in a saturated filtration bed. Those bacteria digest the soap residue, body oils, and organic particles in the incoming greywater before the water percolates through the lower gravel layers and exits into the distribution system. The plants are not just decorative. They are doing active biological work that makes the entire system function. The specific plants suitable for this role vary by climate zone. In the American Southwest, bulrush and certain native sedges are the appropriate species. In the Pacific Northwest, cattail and common reed perform the same function. In subtropical climates, papyrus and water hyacinth can be incorporated. The selection matters because the root architecture determines how effectively the aerobic zones are maintained in the filtration bed. The wrong plant produces a filtration bed that goes anaerobic within weeks, creates hydrogen sulfide odor, and begins bypassing biological treatment. The right plant produces a bed that improves in treatment efficiency over time as the root system develops and the bacterial community establishes itself around those roots. The physical construction of the filtration bed, the sizing calculations that match the system to the household gray water output, the pipe configuration that distributes filtered water to the garden through subsurface irrigation, and the regulatory considerations that determine what is legally permissible in your specific jurisdiction before you begin cutting into drain pipes. Those are the elements that determine whether this system delivers on the extraordinary promise that gray water represents for drought-affected gardens. All of that is what Part 2 covers in complete practical detail. The construction sequence matters as much as the materials because a gray water system built in the wrong order creates problems that cannot be corrected without dismantling completed work. Build the filtration bed first. Connect the household plumbing second. Install the distribution system third. Commission and test in that sequence, and the system comes online without the biofilm buildup and pipe blockage problems that plague systems built without a functioning biological layer already established before the water load arrives. The filtration bed is a watertight container, typically a lined trench or a repurposed food-grade intermediate bulk container, sized at a minimum of 1 gallon of bed volume per gallon of daily gray water input. A household generating 60 gallons of gray water daily needs a minimum 60-gallon filtration bed volume. Upsizing to 90 or 100 gallons of bed volume gives the biological treatment community a longer hydraulic retention time that improves treatment quality and provides capacity buffer during high-use periods like house guests or heavy laundry days. For a trench-based system, excavate to 18 inches depth and line the trench with a 40 ml EPDM pond liner or a 40 ml HDPE liner. Either material is chemically compatible with the soap and detergent compounds in gray water and has a documented service life exceeding 20 years in buried applications. Overlap the liner at the corners rather than folding it because folds create stress points that crack under the lateral soil pressure of a filled bed. Fill the lined trench in 3 distinct layers. The bottom 6 inches is washed drain gravel, 3/4 inch size, which provides the free draining zone where treated water collects before entering the distribution pipe. The middle 6 inches is coarse horticultural sand, which provides the primary physical filtration layer where larger particles are removed from the water column. The top 6 inches is a mixture of 60% fine sand and 40% finished compost, which provides the biological substrate where the wetland plant roots establish and where the aerobic bacterial community responsible for organic compound digestion develops. Plant the wetland species directly into the top layer at a density of 1 plant per square foot of bed surface area. Water the plants from above with clean municipal water for the first 3 weeks before connecting household gray water to allow the root system and bacterial community to establish before the organic load arrives. A biological filtration bed that receives gray water before its treatment community is established goes anaerobic immediately and produces the sulfur odor that makes neighbors and family members declare the entire project a failure within the first week. The 3-week establishment period is not optional. The household plumbing connection depends on which water sources you are diverting. Shower and bathroom sink connection is straightforward in most houses, because the drain from these fixtures runs to a single branch line before connecting to the main sewer stack. Cutting into that branch line and installing a 3-way diverter valve allows switching between sewer and gray water system. The diverter valve costs between $30 and $60 at any plumbing supply store and requires no specialized tools to install beyond a pipe cutter and standard compression fittings. Install the diverter before the branch line connects to the main stack so that the valve can redirect flow to the filtration bed without any back pressure from the sewer system. The inlet pipe from the diverter to the filtration bed needs a minimum 1% slope toward the bed for gravity flow. Gray water systems that rely on gravity rather than pumping are dramatically more reliable because there are no mechanical components to fail during the extended drought periods when the system is most critical. Size the inlet pipe at 3-inch diameter minimum to prevent blockage from soap residue accumulation. Install a clean-out access point at the highest elevation of the inlet pipe so that any accumulation can be cleared with a drain snake without disconnecting the plumbing. The distribution system that carries filtered water from the bed outlet to the garden uses standard half-inch drip irrigation line buried 4 to 6 inches below soil surface. Subsurface distribution eliminates evaporation loss, prevents surface pooling that creates human contact risk, and delivers water directly to the root zone where plants can use it immediately. A simple gravity-fed distribution system using a header pipe connected to the filtration bed outlet and branching into individual drip lines across the garden bed requires no pump, no controller, and no electricity. The water level in the filtration bed rises with each household use event and drains continuously through the distribution system into the garden soil. The regulatory question must be answered before cutting into any drain pipe. Arizona, California, New Mexico, Texas, and Montana all have established residential greywater permitting pathways with straightforward approval processes for systems meeting specific design criteria. Most permit requirements specify subsurface distribution, no kitchen water inclusion, and minimum setbacks from property lines and water features. The permit application in most of these states costs under $50 and is approved without site inspection for systems meeting standard design specifications. The system that costs the Phoenix family under $300 in materials is producing 60 gallons of filtered irrigation water daily from water the household was already generating and discarding. Across a 90-day drought restriction period, that number represents 5,400 gallons of garden irrigation delivered at zero marginal cost after the initial build. At current Phoenix municipal water rates, that represents over $80 in avoided irrigation expense from a single summer season. The system pays for itself before the first drought ends and produces free irrigation water for the remaining life of the property. The garden that stayed green on the corner lot was not lucky. It was built. Thank you for watching this video. Click here to watch another video that might interest you.